welcome to our session on performance tuning for low latency workloads in SUSE Telco. I hope you're having an amazing time at SUSECon. Thank you for joining us here today. And before we move forward, I figured that we'd do a quick introduction. My name is Rob Bonilla. I am a Director of Engineering Programs. I try to work very closely with the Edge group and other business units within our company, sort of a bridge between all the way from customers back to engineering, and hopefully doing everything we can to try to build the best products that we can. My partner Alberto is here.
Yeah, my name is Alberto Morgante. I'm Principal Telco Engineer working for the Edge customer. I'm focusing our effort helping our customer in the telco world.
So very quickly, I wanted to try to jump into our agenda. We will start with some basics on why low latency solutions. I'm sure most of you are familiar with that, but figured it would be worth going through it. We will then move into some best practices, which will include kernel arguments, timers, moving into BIOS, performance configurations. We'll also discuss useful networking tweaks that we have found over time have been beneficial to our customers, and all while sharing how each tuning parameter has helped us achieve low latency solutions within Telco. We'll wrap it up. We'll share some of the testing results that we did. I think that's extremely important to understand that a lot of the work that we've done has been specifically for Telco customers we have. This, of course, means that you'll have to make tweaks for your own environment, but we'll go into more details about that later. And then, of course, we'll end up with some key takeaways and some questions, okay? So let's go over some of the reasons why low latency configurations are beneficial. We know that low latency tuning focuses on minimizing the time between an event happening, such as receiving a packet or processing input data, and we try to tweak it so that we can lower the system's response for that particular event, whether that's sending a reply or writing to the data disk. This is especially important when it comes to Telco 5G. We want to reduce the time spent in scheduling interrupts and context switching, okay? So what we want to do is reduce the time spent in scheduling. We want to prioritize predictable and fast responses, and we want to mostly minimize the unnecessary work that our kernel is doing in order to improve our speed. All right. So before we move forward, though, as Alberto and I were talking about the session, we figured there may be some people in the crowd that are also interested in tweaking the kernel towards other pillars or workloads. So by a quick show of hand, we know you're interested in learning about how we tweaked it for Telco, but is there anyone else here that's in other areas such as maybe industrial IoT, retail, medical, or any other area that you would be interested in learning about tweaking the kernel? We'd like to ask these questions because obviously it helps us towards possible future sessions, etc. Anybody interested in another area?
IoT is a good use case.
IoT? Thank you. Anybody else?
Yeah.
Just general kernel tweaking?
Yeah.
Awesome. We'll definitely go into that, so thank you. I appreciate your feedback. Okay. So, now that we've covered the, some of the reasons why we're going into that, when we're talking about real-time communications, we're talking about instantaneous or near instantaneous transmissions of data, voice, video between devices, users, and systems, right? Both Telco workloads and 5G are typically designed to deliver ultra-low latency. So this enables real-time interactions between devices. Low-latency kernel configurations obviously play a key role in this, ensuring the packet processing and scheduling and network stack operations happen with minimal delays. We'll discuss how we can accomplish this by reducing kernel scheduling latency and optimizing CPU affinity running on dedicated cores. Edge computing, which is the area that we mostly work on, processes data closer to the user, of course, and reducing that latency associated with sending data back to centralized servers. This enhances real-time performance for applications such as augmented reality, virtual reality, cloud gaming, but of course there's going to be other areas that are going to benefit, such as telemedicine, smart cities, smart manufacturing, and as you stated, IoT. We'll also talk about network slicing and QoS. Network slicing allows our 5G operators to create dedicated virtual networks with specific performance requirements, and quality of service mechanisms ensure high priority traffic is processed before less important data. So for instance, making sure that you're giving priority to time-sensitive applications such as voice over IP, video calls, over less critical traffic, perhaps somebody's file download in the background. Optimizing queues and packets, schedulers minimize latency, while preemptive kernel enhancements, which is a lot of what we'll discuss, improve real-time task execution. IoT and massive device connectivity. You know, Internet of Things networks must support millions of devices at this point. A lot of people take that for granted when they're using their devices and they just think magically the data comes back and forth. Low latency ensures that devices respond instantly to these events, minimizing network congestion. Optimizing IRQ handling and CPU isolation further reduces jitter, improving the real-time performance. So fine-tuning system timers prevent unnecessary delays, and we will go over all of that. So it's important that we talk about some considerations. Again, I'm sure most of you are aware, but just to be clear, you know, what we're going to present is obviously not a universal performance guide. A lot of that is going to depend on your environment, right? And what we mean by that is the recommendations that we're making are specific to customers that we work with. Of course, we had to take into consideration everything from applications, the hardware, the BIOS, anything like that can change the way the setup is going to go. So, but what we wanted to do was try to provide a guide that would help you at least get a base towards getting under 10 microseconds. So of course, factors like IRQ handling, timers, CPU isolation, kernel arguments, and other areas that we just discussed, right? So please keep in mind that while some of the tuning depends on hardware and workloads, what we wanted to do was just provide that solid foundation to get you started. So for the next slide, I'm going to go ahead and hand it over to my very capable colleague, Alberto.
Yeah, thank you, Rob. Yeah, so I think as you say, Rob, the most important part is keeping in mind that there is not only one factor that you can work on, try to improve your platform to get the best latency for your workload. So I think it's a combination, and the important part is that depending on your needs, sometimes you have to do one kind of customization for the kernel arguments. For example, this is the first part that we are going to cover. But this, depending on the use cases and the workload that you have on top of that, maybe could be different in another one. So we're totally sure we have different customers that may be using a specific configuration for kernels, as we are going to see. Has a really good performance, but also is depending on the application that you have and the typical things that you never consider at the beginning when you are deploying the application. But for example, for the DX, IoE, EO, so it's complicated to know how is the best way to perform, to tune the system to get the best performance on the low latency for that application. So this is something that mostly covered the first list of the kernel argument that we started working on SUSE Edge for Telco 3.0. So at the beginning, we thought that this was the perfect low latency performance to get with our applications. But during the journey that we've been doing for 3.0, 3.1, 3.2, we've been discovering that some kind of these parameters could be improved. And for sure, receiving some kind of feedback from customers and also internally working with kernel people at SUSE, we decided to modify it a little bit, just some kind of changes. So as you can see, there are some modifications that we've been doing. I'm going to go through all these changes in order to get the final version that we have now. But repeat again, we said at the beginning, it's something that you could use, but you have to take care that is depending on the application and also the hardware that you are using, as well as the different needs that your application is required for a low latency performance. So we are going to go through some of these kind of parameters just to get into the details and to explain a little bit what does it mean and why we decided to use that. So the first one is we decided to remove the Intel P state because this option is like it's a driver which is used for manage the power and the performance for the CPUs. But however, enabling these options, at the end of the day, we are disabling the hardware P state. So it's good or it's bad. So if you are doing on the software layer and the operating system layer, it's better or it's worse than if you are doing on the hardware part. So but in my opinion, it's depending on your cases and the vendor that you are using, because not all hardware vendors are using exactly the same implementation. Yeah, sure.
Sorry to interrupt. So while we're having this discussion, are we primarily talking about physical instantiations of boxes or virtual machines or containers? Are you talking about the container operating system?
Yeah, so basically what we've been working on that is for the container part and also for the workload that we have running on Telco, that basically are CNF application running on top of that. So depending, for sure, is the most important part. As you say, depending on the use cases that you are applying, some kind of these parameters are not good, and we have to remove from the list. So it's not a universal guide, and the good thing is that we would like to show what is working fine for us to get the low latency parameters, but also maybe if you are using a different workload or different use cases, that kind of customization are not so good and you don't have the best performance. So for this kind, this is the first one. So what we decided is to use the hardware P state. But again, we started with a different project at different customers, and we decided to do exactly the opposite on that. So it's not something that we will say something just for all use cases. The important is to understand how we are able to do that. So we have different mechanisms and SUSE that we could configure with the CPU frequency set to the performance. And depending also on the hardware, in the combination with both parameters, you will get the best performance on that. This is the first parameter. The second one is just an improvement, because at the beginning we were started using the processor match C state and the Intel idle C state. But then we changed for the idle pool because disable the CPU idle state completely. The CPU never enter in a lead state, so it remain always with the full power. So for sure, this is something you can also configure inside of the BIOS, and in my opinion, this is something we have to keep in mind just in combination with different layers. So what we mean is having different kind of variables. Sometimes it's better just to do it on our operating system, on the operating system layer and or kernel, maybe, and sometimes it's better just to have directly by the hardware vendor.
When you changed the CPU idle pole and you had it completely removed the idle states, did they have any issues with it creating more heat or any kind of problems like that for the particular system?
So for sure. So if you remove the time that they are sleeping, means that the CPU has to be full power all the time. So for sure, it's going to increase the heat generation that you are having in the data center and also the consume that you have. But we are assuming that this is for a telco workloads. So basically on this scenario, the important part is the performance and the high profile performance to get the best, the low latency as possible. And in this case, it's not, this parameter is not the most important, so heat generation could be covered in a different way.
Gotcha.
Yeah. So sometimes you cannot use the idle pool for all parameters. So there is a different way to force just only one specific CPU to get the minimum values for that. So again, depending on the way that you are defining your application, depending on the needs that you have for your performance, you could say, I know that this CPU is pinned to a specific workload, and we have to reduce the latency and configure only this CPU for this part. So we are able to configure in a different way. So it's all the time the same decision that you have to do. It's a trade-off between the common things that you are using between the things that you could customize just only for specific things. This is an interesting parameter because at the beginning, to be honest, I didn't know. Working with kernel people, you always learn really, really good things. So we were using kernel thread CPU parameters, and it's mostly used for all distributions, all vendor distribution, but at SUSE, the SUSE kernel never include one of the patch, which is included in these parameters. So at the end of the day, we don't have this out of tree patch included in the SUSE kernel, so it's not needed. So what we are doing is just removing from the list because we are including in a different way, which is the no edge full kernel parameter to do exactly the same. So basically, as you can see here on the next one, we are doing the no edge flag in order to stop the scheduler tick that usually is running on edge CPUs. And the tick is because we removed the previous one, so we have to include it on the ISOL CPUs as a flags. So this is the configuration for the flags for the ISOL CPU in order to configure exactly the domain and the number of CPUs that we are going to isolate it from the rest of the one, just to make our workload to be pinned to this CPU. The last part is the manage RQ, which is included in this ISOL CPU parameter as a flag to say to the kernel which is the CPU that has to be responsible to manage and to prevent to manage the IRQ, and preventing that IRQ will be moved to a different CPU. This is really important, and sometimes it's a really, really complex things to do, because when you are defining your application, the problem is that you could imagine that it's going to be pinned to a specific CPU. The problem is that sometimes has a different DIX IOs, and you cannot control where is going to happen the IRQ. So with this parameter, you are able to at least limit the number of CPUs that is managing the IRQs, which is something that is increasing a lot the latency in the applications. So with this parameter, we are able to reduce the number of CPUs that they are going to have interruptions, or maybe they are going to have handled the interruptions, and the latency is really improved. The next one is the watchdog that some kind of a system, well, all Linux are having internally implemented in the kernel. So there are some kind of mechanisms that you are watching for different errors and different kernel crash or something like that. But keeping in mind that this is something not good, keeping in mind that this is something not good because we are losing some kind of traceability and maybe observability. For a telco, from a telco perspective, what we want to do is just to optimize and to improve the amount of CPU cycle that we have to dedicate to the workloads. So one of the recommendations is just to remove that if you are sure that some crashes will be controlled from an external point of view and not having these kind of messages in the kernel. So again, it's depending on your needs. If you need to have the traceability and you have to take care about the kernel crash and all the things that we could have with these parameters, you should keep it. But if you are able to control your system, and maybe as we are doing with SUSE Edge for Telco, which is deploying one server, and we are able to auto-deploy again just to have it as a backup, in my opinion, this is something we can remove and just to improve the latency that we are having. The timers. So this is something really complicated. I have a really good friend at SUSE working on that part in the kernel, and he created a really good article. So if you have time just to see, to take a look, is something that is really interesting. So timers are complicated from a low latency performance point of view, because sometimes the timers are introducing kernel cycle, CPU cycles, which is involved inside of the kernel task. So sometimes when you are having a periodic ticks inside of the CPU, you are reducing the amount of CPU that you are able to dedicate to the workloads. So basically what we are doing is dealing with three kind of timers. The first one is the periodic kernel timer, which is by design, the kernel is designed with these periodic timers. But also we have external timers which give us the possibility to control the system, like systemd timers, these timers. But also we have the hardware timers, which maybe if you are involved on precision timing protocols, you will have these kind of timers also that we could increase the latency that you are having on your workload. So what we could say is that basically for the systemd timers, they are introducing a lot of CPU cycles which are not necessary. So sometimes what we are doing is just to remove the list of the timers that we have on the systemd. This is something that at the beginning, to be honest, I was not able to imagine that it was improving the latency, but after testing that with the kernel guys, they decided to remove that, and when we tested again the performance that you are going to see after that, we increased a lot the performance removing the latency that we have. The second one is the timer migration. So it's important to know that sometimes you have different kind of timers that maybe could be moved to a different CPU. So remembering the isolated CPUs parameters, you can imagine that if you are trying to isolate your CPU just to be dedicated for a specific workload, if you have timer inside of that CPU, it's going to be a problem. So if you are reducing the time, if you are disabling the timer migration, you are sure that no timers is going to come to this kind of CPUs isolated. Oh, sorry. And the last one is the virtual memory stats updates. So from time to time, the kernel is saying to the, it's checking the memory in order to know the statistic. So by default is, if I don't remember wrong, is every second. So every second you are having cycles of CPUs that they run in these kind of timers to get the information about memory. So one of the things that we can do is just to delay. We are not able to disable, but we are able to delay that kind of measures. So for sure, if you are delaying that point when you are having cycles, CPU trying to get that statistic, you are reducing the amount of time that the CPU is working for the system instead of the workload. BIOS and performance. So this, to me, is the most complicated part to explain. We were talking last day, preparing the presentation. And to be honest, this is really, really dependent on the hardware. So some kind of vendors are preparing the BIOS for a specific profile, which is really good because are preparing the hardware to have a telco performance profile inside, and maybe they are improving the hardware to work this kind of workloads. But at the same time, it's complicated because you have two different layers. One of them is really, really accoupled to the hardware, and the other one is really decoupled to the hardware in the operating system and maybe on top of that. So you have to combine, and you have to know what is happening under the hood with the BIOS configuration that they are preparing to optimize the hardware, to understand what you have to do on the software layer to combine both and just to have the best performance.
So before you move forward,
yeah.
So one of the things that I found, he was teaching me all kinds of stuff, is that if you make the changes to the kernel parameters, but then you change your BIOS, it can actually overwrite some of those parameters, right? So back to the tweaking part, and I'm sure a lot of you have probably the same questions that come to my mind. I look at it from the perspective of, I like to modify cars, I like to make them faster. So what price am I going to pay, right? You put a turbo, you put more boost, this how much does my engine last? So when you talk about the timers, did you get to a point where you pushed the timers so much that then it caused issues with the system? And that's how you found that I guess what we would call that sweet spot, that perfect place where the timer is just right? Because it sounds like you're removing a lot of things from the system, which we would typically see as either safety or logging, such as a kernel crash and things like that. And I get it that they have the hardware and they're willing to sacrifice that. But did you run into any of that?
Yeah, absolutely. It's a trade-off. So sometimes you are trying, and if you want to optimize the performance and the low latency that you are, or try to get low latency as possible, you find some kind of difficulties and problems during the journey because you are enabling something that you think that is working fine and is really, really useful, but at the same time, if you are changing something in the other layers with the timers or the software part, you are getting bad performance, and you cannot understand why it's happening. But it's the combination of all layers, and just to try to, to think what is happening. You're going to see now, after that, during the test that we did, that basically is try and error sometimes. You have to put it 24 hours, the performance, and just to get the information that you're receiving from the kernel, all the calls that you have, and just to say, okay, I know that here there is a DX IO interruption, and I have to identify which kind of workload is creating that IO. And we have to think how we are able to modify the kernel, maybe the combination of kernels, timers, IRQ, whatever, just to have the best performance and reduce this kind of IOs. It's complicated. It's a complex.
And I think you also mentioned that you also had to figure out how long to run it before you could actually trust what you were seeing. And went from like 4 hours to 24 hours. What was the typical time?
To be honest, it's not the same. When you're starting, maybe you could have 4 hours with the best performance, and you say, "Oh, I'm doing really well, so my manager is going to be happy with me." But at the end of the day, it's difficult because 24 hours are really, really, a lot of time to have something like an interruption that is going to get more than 10 microseconds in the latency.
And I know you're going to show it later, but what I saw was you might run 6 hours beautifully, and then something would really spike up, right?
Yeah, we will show there.
Okay,
yeah.
okay.
So basically, in the BIOS configuration, we are putting focus on the CPU power management, memory and the cache settings, and the RQ timers, for sure. There are other kind of parameters which are also important, which is the fan speed and mixed LNU configuration that most of the vendors, they are having inside of the BIOS. Because you are thinking that, the fan speed is not important, but at the end of the day, CPU is running full power, and you need that the fan will be at the same time. It's like in a car. You have a car. If your engine is going to the limit, you have to have a really good air cooling system just to get the best performance at the same time. So it's interesting just to how we are able to combine all of them. Yeah, Nicola.
So you said that the vendors sometimes have profiles. Did you have any issue with those, like not being documented or not being detailed enough of what they do that it brings you issues when doing the other tweaking?
To be honest, the answer is yes, because they are documenting, but it's really complicated what exactly is happening when you are applying this profile, because it depends on the layers that you have on top. So maybe they could test it, that kind of profile in a specific system with a specific workload on top of that, and when you are going to your environment, it's different, because you don't have maybe you could have the information and the documentation is also available. The problem is how you are understanding that in our combination with the stack that you have on top of that. So sometimes it's difficult, yeah, for sure. The CPU power management. So basically what we are doing is disable the typical things. So this is really, really common in telco. So it's disable the C states, also P states. And if it's available, enable the hardware P state mode, depending on the need, as we saw before. Maybe it could be helpful also. Turbo boost is something really curious, because I have to be honest, and I was thinking that turbo boost, when you heard turbo, you say that everything is going to be faster and the CPU is going to, to be better. But sometimes the turbo boost, we discovered that could introduce some kind of unpredictable latency, because he's trying to get to the to the maximum velocity of the CPU. But at the same time, who or how is controlling this kind of velocity? So the process that is controlling this kind of process to maximize the CPU is exactly who is introducing the latency at the other side as a side effect. So it's complicated sometimes just to get this parameter enabled. Our tested, the test that we did basically were better disabling tubal boost. And the last one is something which is a recommendation, which is the hyperthreading to make it disabled, but sometimes, depending on the application, you cannot do it. So, for example, I remember that we are testing, I don't want to say names, but we are testing a very famous application to test if your platform is capable to run Telco workloads or 5G workloads on top of that. And during the test, we discovered that the application was not prepared to running without this option, because they were working with hyperthreading. So again, the ideal is try to disable, but depending on the workload that you are using. Related to the memory is something really, really curious, because the typical thing that everybody knows is just to enable the NUMA. But at the same time, enable the profile to the performance profile of the memory to maximum. But there is a parameter, or there are some kind of parameters which are always the same goal. All of them has the same goal, which is the prefetch. So by default, my recommendation on what we tested and it was working really, really fine is disable any prefetch. Because the time that you are getting to load or preload the information in the memory is time that you have also to manage with the CPU, and also it will be closed because of NUMA, but at the same time, you will increase the amount of latency that you are generating on that. So the prefetch are okay for some kind of uses, but for a telco workload, you don't need to prefetch because it's really, really fast processing. And having the NUMA enabled, what you are doing, enable the prefetcher, is just adding new latencies to the system. This is something that maybe could be, there are really a lot of parameters related to the RQ and timers. But for some time real-time application, the time step counter sometimes is better than having this hardware timing protocol. So depending on the use case, it's exactly the same. One of the most important part, in my opinion, and after testing that in the environment, we discovered that the fan speed that I explained before was important. But also, the telco profile is really, really useful when you don't know how to start to tune in the system. So at the beginning, my recommendation is just to start using the performance profile that most of the vendors in hardware are enabling that, because it's a good starting point. You could start defining the telco profile and just seeing what's happening with your application, running a test over 24 hours, and after that, just get the output. If you see that you are having a lot of interruptions, maybe the most important part is just to discover why you are getting those interruptions instead of changing all parameters without knowing what is happening under the hood, right?
This one surprised me a little bit. I mean, something that surprised me was that a lot of the features that you're saying to disable, to me, in my mind, I thought they would actually be helpful, which you already covered some of that. But the other one was that you can make the changes to the parameters, then change the BIOS, then it overwrites this. So do we recommend that people look into the BIOS area first?
Yeah, absolutely.
Okay.
Yeah, for sure. I have the experience working with different vendors, and at the beginning, the same parameter that we have automated with SUSE Telco for Edge, kernel arguments, the different things that we are automating on the software layer, we tested on a different hardware, and the result was totally different. So it's It's not a problem on the workloads. It's not a problem on the software, on the operating system. It's just a combination of all of them just to get the best performance.
So right after I talked to you about this, I was on the floor out there talking to the different vendors, and I realized Oxide has tried to get around some of this by just, they don't even have a BIOS anymore. And of course, they have all the fan systems set up so they can handle the higher performance, right?
Absolutely, yeah. This part is also interesting because, you know, when you are working with a latency, maybe the problem is not just only this latency that you have in the CPU and so on, but also you have to keep in mind that the networking part is really important to get the best performance as a, you know, for your workload. So this kind of networking tuning is basically what we are trying to do is just to get the maximum amount of data possible, reducing the time that we are trying to or spending transmitting to the receptor. So I think with this one, what we are doing is trying to optimize the UDP socket buffers with the read memory max and the write memory max. We want to, you know, to make it larger, just to have less time doing the transaction on the CPU. Will we avoid dropping some kind of packages? Here is the same. So basically, what we are doing is trying to upgrade some kind of optimize some kind of parameters that by default in the system, like for example the max backlog, which is controlling the queue that we have for the incoming packages. So if you are if you are having a really small queue, the number of packages that they are going to come is smaller, so you are going to deal with them more time than if you are increasing the time. So basically, this is some kind of customization that we have on the network. I'm going a little bit faster because we don't have enough time. So I think the important part also is just to share with you the testing that we did and the conclusions that we have. So in order to test it, what we did is basically using two tools. The first one is the cycle test, which is part of the RT test packages. Basically what it's doing is including some kind of high priority task in the system, and it's trying to know which is the time that you are spending in the CPU just to get answer. So basically doing that on different kind of CPUs, as you can see in the command, you are getting the real measure of the latency that your system is having for that. So there are some kind of parameters which are really important. For example, the priority that we are measure, which is 98, the number of threads that we have, which is the affinity of the CPU that we have. So remember that the affinity is the CPU that we configured on the isolated cores for the kernel parameters. So basically, what we are checking is we don't need all the information for all CPUs. We are going to test the latency only on the CPU isolated cores. The interval that we have, the isogram, because after that you will see we are able to generate some kind of graphs to know more about how it's happening in the system and the spike that we have and the duration. The second one is the RT app. So what we try is to use a generic real-time application in order to avoid having the typical problem that in my local is working fine, you know? So it's something really, really common that you are testing something with your application, and when you are putting on a customer, the customer application is different and the performance is also different. And the result for sure is gonna be a complete disaster. So what we tried is creating an application which is based on the RT app, and we were able to define a JSON file, which is included in the app for sure, but trying to define a JSON file to specify the amount of CPU and the percentage of CPU that we want for each one, for all CPUs that we have in the system. So at the end of the day, we are creating a profile to test how to create a behavior about the system and how we are able to deploy some kind of application if we are able to run on a different system. So as you can see here, for example, what we are doing is for all CPUs, isolated CPUs, we are putting the load to a 95%, and we just having only a sleep for 5 microseconds. So basically what we have is mostly the CPU loaded for 97%. This is really cool because we don't need to have an application running this kind of test. So we can use this simulator to have every time the application running, depending on the duration that we have, or there are different kind of values that we can use. So with the combination of both, this is what we had at the beginning. The first one, as you can see, without any tuning, without any performance optimization, without any kernel, having just the system from the vendor, putting the operating system, the Kubernetes part, and just without any tuning that I explained it before. As you can see here, the latency after 24 hours, the latency was, the maximum values was 215 microseconds. So for a telco workload, it's really, really complicated to work with these kind of values because they are really, really sensible to the latency. So after all tuning that we did, the maximum was 6 microseconds after 24 hours. So I think it's an incredible value. It's not easy to get, so there are some kind of people in the room that know that it's complicated to achieve these kind of values. But at the end of the day, the most complicated part was the amount of time that you spend trying to know how your application is designed to optimize the system. So, Rob, this is the conclusion.
Yeah,
what do
that
you
was
think?
impressive.
Yeah.
I want to make sure they have time to ask questions. So, of course, we have to reiterate that this is all dependent on the applications, the hardware that they were running, and Alberto did a lot of hard work collaborating with our customers and partners towards achieving some of these goals. I feel like we've sort of highlighted those areas, so I don't need to necessarily repeat that. Again, highly dependent on both the hardware and the real-time applications. I do have one question that I should have asked you before. Since you were making changes, is that going to be, are we going to make this available to our partners and our customers sort of as a basic guide? And is that kernel specific? In other words, it's going to be a specific version before they can implement some of these changes?
Yeah, so basically, I think it's really, really difficult to provide a guide, like a universal guide. So it's complicated because it's depending, as you saw, it's depending on a lot of factors, and it's not all of them are under our control. What we are able to do is just creating some kind of scripts, performance script that we named, that basically trying to optimize if the system is not prepared for that on the software layer. So I mean, we're trying to optimize the UDP packages also. The networking tweaks that we saw is something that most of the telco customer has to be configured, but also the CPU performance script, part of the things that we saw are included in the 3.2 releases. Not as a, the important part is maybe it's not useful for all of them, but it's not doing nothing wrong in the system.
It gives them somewhere to start.
Yeah, exactly.
Yeah. So yeah, that's kind of what I wanted to highlight. So of course, we want to open up the floor to any questions you may have. Yes, sir?
No, just only one question, because I think it's important. Just this is not only my job or the rest of the team. So we've been talking with other internal people in the kernel team. So it's really, really appreciated just the help that Peter and Mel Gorman give us in order to improve everything, because it was really, really complex at the beginning, and thanks to them. So they are not present here today, but I would like to do the kudos to them.
Awesome. Yeah, go ahead.
The results you obtained in the optimization of the latency are quite impressive. And I want to ask if you had the chance to verify on a real application. I mean, for example, I think that a virtual DU for a RAN system could be a good application for verifying if the optimization of the performance used in
Yes.
the real application are similar to what you obtain with your test
So-
application.
Yes,
or
that's
it
that's
So the question is, have we had a
Yeah.
chance to test it on real-world applications?
Yeah, that's really cool because we were working with different telco operators and also different customers. So at the beginning, most of this kind of configuration are on the customer side because they know exactly which is the application that they are running. So for sure, the customization at the end of the day is going to be there. But after having some kind of conversation with them, when we tried to generalize or industrialize this kind of performance testing, we were talking with them, and surprisingly, they were doing mostly the same things that we are offering here. So, and they are also under 10 microseconds. So for sure, depending on the hardware, maybe some kind of parameters were different, but mostly, most of the things that we are doing here was being done by them without any.
Yeah, so they
any
couldn't
comment.
provide us some of the information, but they verified that the changes we made were
Yeah.
working for them. Yes?
That's the point. So we have information from two brand vendors that they were able to achieve similar performance levels with similar settings, not always 100% identical. But that was actually also not the point of what we were doing here. What we were trying to achieve here is to understand if all the relevant backports are in our kernel so that we can actually achieve these performance levels, right? So the testing and the configuration is one piece, but in some cases we also have to actually modify the code base for the kernel and make sure that we pull in additional backports or that additional fixes were added to the code base. And that is at the end of the day what this methodology provides us, because we can't do this without running workload on the system. Right? So it effectively guides us in the development of the product, which then gets pushed out to our customers and they can do implementation in their specific context.
Yeah, while we're giving kudos, Tim is our product manager and has been amazing and supportive along the way for this testing to make sure our customers are getting what they need. And of course, Alberto and sleepless nights. Any other questions?
Do you plan to have a tuned profile for the kernel system tuning?
Do we plan to have what?
The tuned
Tune D profile? Do we plan to have Tune
Yeah,
D?
so to be honest, it's one of the tools that we started using. So at the end of the day, TuneD is doing most of these kind of things, but in a profile, So we started using the CPU, the CPU profile just to optimize that, the CPU performance profile and the CPU partitioning profile, both of them. But we started using that, but we decided just to move to standalone, tools or maybe customization because we didn't know exactly what it's doing under the hood. So you know that you have a file with all the things that you are doing, but if you see the things that they are doing for CPU partitioning and the same thing that you are doing for low latency profile are mostly the same. So where is the chain between both of them? So it's useful. So to be honest, this is a really good starting point to start with this kind of thing because you can configure it by default and you don't need to understand all the parameters that you have. But at the end of the day, when you are getting into details and you know more about this, I think it's also useful just to understand what is happening with the different parameters. So.
Since you understood now the parameters, do you plan to have a Telco profile?
Don't say it too late because Tim is here, so maybe we can create a new task in the team. Yeah, no, I mean, makes sense. I think makes sense. And it's also useful just to have a specific profile for that. But also you have to keep in mind that this depending on the workload that you have on top. So if we are saying something just really, really specific to the rest of the customer as a generic point of view, maybe could be, a trade-off. Yeah. Tim?
We do have example deployment manifests that set up the system according to what you showed me, right? So
Yes, exactly.
those are things we are also using in our own test pipelines, right? So there are GitHub repositories which are public.
This is
where
supposed to be
we're
over at
keeping
20 after.
configurations that we run in our own CI, and that's where you will find all these settings, right? So that's where we basically, that's our single source for
Yes.
for this. We're not treating them as reference configurations because what happens in the field is too diverse for that to be
Exactly.
but the information of what we're doing to achieve the results is publicly available.
Yeah. Yes, sir.
Really quickly, we want to make sure you have time to get to your next session.
So has your work primarily been focused on like ORAN and the RAN space, or is it OSS, BSS, and all the network functions as well, like as far as UPF and SMF?
I would say RAN, but
Or would we envision having different profiles based on segregating that workload to different hosts profiles maybe?
yeah. So basically, when you are working with telco, the different use cases are incredible. So you could have DU, RU, whatever, but at the end of the day, the configuration it not could be the same for all of them. So for RAN, maybe some of them could be in a generic wall, but but it's difficult to generalize some kind of configuration for all use cases. I'm not sure if.
Thank you
answered
for
the question.
attending. We hope it's been informational for you.